Good morning again. I'm Jakub. I am the founder of DB Booster. It's an automated index tuning tool for Oracle and Postgres. And just last week, I joined Product Board, which is a former Czech unicorn. It relies heavily on Postgres, and it solves very interesting issues, not only data related. My topic is B-tree indexes and their access paths. And let's jump directly into the sample data. It's a very simple table with movies. There is only 10,143 rows, no constraints, no indexes. There is even no primary key. I will focus mainly on ID, name, and language in this presentation, but there is even more columns than on the slide. There is some revenue, description, whatever, but it's not important. So this is my query number one. I'm interested in movies in Czech, sorted by name and ID, and I'm using the famous select star column as the best practice. And there are only 2 movies in Czech in my database. And I have Postgres version 18. That's very important. This is the actual execution plan. I got it via explain, analyze. Explain, analyze, really run the query and give you the exact statistics, what happened during the execution. I removed most of them. I kept only the interesting one. And I will focus mainly in this talk on the key metric buffers. Buffers tell you how many 8 kilobyte pages Postgres had to touch during the execution, because we store our data in 8 kilobyte pages. As I have no indexes, there is only one choice for Postgres, and that's the sequential scan, which represent full table scan in Postgres. It means that I scanned all the rows from the first to the last. By other words, I scanned all pages allocated to my table. And I return only 2 rows, 2 movies in Czech, and I filtered out 10,141 rows. I believe the inefficiency is obvious. I got 2 rows. I read 357 8 kilobyte pages. So there has to be a better way how to get my data. The best way is to utilize something called CTID or tuple ID or TID. CTID is a pointer to your row. It's a page number followed by slot number in that page. So when you know CTID, you can go directly to the right page and get your row. I have CTIDs for my 2 rows, so if I use them instead of the language condition, I hit only 2 pages. That means that I have bad luck and my 2 rows are stored in different pages. If I am lucky, they can be stored in a single page, and I can hit only 1 page. I forgot to mention in the previous execution plan that there is, of course, sort operation because I have the order by, and sequential scan does not return my data in an ordered way. And it's the same with the TID scan, which replaced the sequential scan. So I have to still do the sort. The key issue is that I don't know CTIDs for the rows I'm looking for. And that's when B-tree indexes come in. B-tree index simply maps key values to CTIDs, so some indexed columns to the pointers directly to my table. So let's create an index for language, name, and ID. You can visualize your leaf level using query like this. You just put the indexed columns in the select clause and in the order by clause. If you define your index with some ascending, descending order, you have to reflect it in the order by, of course. So this is how the leaf level looks like. It's just accept, of course. And I want to point out that, for example, the name is ordered just for one particular language. So my names are ordered for Arabic movies. If I switch to Basque, the name starts over. If I switch to Bengali, it again starts over. And it's the very same with the ID. ID is sorted just for the language and name pair. So, as I mentioned, this is a leaf level structure. The leaf level structure is linked into a double linked list, so I can easily back and forth. And we built a real tree structure upon our leaf level. In this case, it's 3 levels, the root level, 1 intermediate level, and the 1 leaf level. And to get the first index entry matching my criteria, I need just simply read the number of pages equal to the number of levels in my index. So in this case, I need to read root, 1 intermediate level, and 1 leaf page, and I have the first index entry which is matching my criteria. If there is multiple index entries matching my criteria, I simply scan the rest of the page and I can jump to the next page so I can get all index entries which are matching my criteria. So these are some fundamentals to be on the same page, and we can go to the next execution, this time with the index in presence. As I have only 10,000 rows, the index height, the number of levels of my index, is just 2. So I need just 2 pages to hit the first index entry matching my conditions. I rerun the query, and this is the execution plan. Postgres used index scan, and I hit only 4 pages. 2 for index traversal, and because I have the star, I need all the columns, and in my index, I have only language, name, and ID, so I need to do a table lookup for every row to get the rest of the columns. And because my 2 movies in Czech are stored in separate pages, I need 2 pages for the table lookups. So I have 2 for index traversal and 2 for lookups, so I end up with the 4. Let's say that I'm not interested in movies in Czech anymore, and I want movies in Japanese. I have 704 movies in Japanese, which is significantly higher. And I forgot to mention, by the way, that index scan, and this is important, returns my rows in sorted order. So they are sorted, so I have no sort operation. That's a key feature of index scan. It returns your data in the index order. So let's go back to movies in Japanese. There is 704 of them. And because it's more rows and Postgres prefer optimizing the access, it uses bitmap index scan. Bitmap index scan is followed by bitmap heap scan. So in this case, the table lookup is separated and reflected directly in the execution plan. In the case of index scan, the table lookup happened, but on the background. You don't see it directly in the execution plan. But with the bitmap index scan, I see it. What happened on the background? I hit the first movie in Japanese. That's to read. And because I have 700 of them, I scan the next pages to get all the entries for movies in Japanese. That's another 6. So I reached in total 7 pages on the leaf level and 1 root. So that's the 8 on the very last line. I built a bitmap of these pointers and then used the bitmap heap scan and touched 306 pages. It's coincidence, and it's again bad luck, that my 700 movies are spread across the majority of my pages. So this is the first key point, that the performance is not led by the number of rows you return, but the number of pages you touch. 700 in 10,000 rows is 7%. 306 from 357 pages, it's, I don't know, 85%. So I touched 85% of my table to get only 7% of the rows. And I still had to add the 8 pages from the index. So in total, it's 314 pages to satisfy this query. So it's still better than sequential scan, but not so much. And again, bitmap heap scan and bitmap index scan need sort operation. So then I sorted all these movies. If I switch to movies in English, that's the majority of my movies. And in this case, I use sequential scan again. It's because sequential scan in this case is the best option. Because if I use the bitmap heap scan and bitmap index scan, I would read most of the index and with high probability all the pages from the table. So if I put together, it would be higher than 357. So sometimes it's sequential scan simply the best option for you. And the point is that the column itself does not tell you if your condition is good for indexing or not. It depends on the value, because I used 3 different values and I got 3 different plans, and all was perfect. And as usual for sequential scan, you need the sort. I'll go back to movies in Japanese, and I would like to get movie called Yojimbo. There is only one movie with this name, and Postgres reflects this in the execution plan, and it uses index scan again. What happens? Because language and name are in my index, Postgres directed down to the first movie with the name, with the language Japanese and name Yojimbo. That's 2 pages, table lookup because of the select star, so I end up with 3 pages. If I look for this very same movie, but instead of name, I use its ID, the execution plan is same, there is index scan, but the buffers are 9. Any idea why? Yes, there is a gap in my index, and it works in the way that I jump to the first movie in Japanese, read all of them, which is 8 pages on the index level, and for every one index entry, I use ID as a filter. So I check ID for every of these index entries. I found one and do one table lookup, so I end up 9. The bad news is that in execution plan, you have no idea that there is a gap. If you don't see this index, you have no idea. People usually compare estimate and actual rows, and it's perfect, 1 and 1, perfect match. There is no row removed by filter. So only sign in this case is that I touched 9 pages to get one single row, and my index height is 2. But in more complex queries, you usually don't see this discrepancy between page and number of actual rows immediately. So it's your job to find out that your index is suboptimal, and you can speed up this operation by removing the gap. And now I behave more like a human, and I switched from the star to name and ID in the select clause. And I go back to my movies in Czech, which are only 2 of them. And because I satisfy all the columns in my query by the index, my index is covering 1 suddenly. And to get my 2 rows, I hit 3 pages. 2 of them for index traversal, and there is 1 more. When you are using index-only scan, your data are sorted. That's the first feature. And the second is that you don't need to do table lookup because you have a covering index. But because of Postgres multi-version concurrency control implementation, you can still sometimes need to check the table to check if the index entry is visible for the end user or not. It's reflected on the line 3, index heap fetches, but it's 0 in this case. So I didn't touch the table at all. Do you know what's the third page? Sorry? Yeah, it's visibility map, because to avoid these heap fetches, you need to check if your rows are visible. So there is something called visibility map, stored again as a page, and you need to hit this visibility map page. This is the last query in my presentation. Select star again, and I want the movie with name Yojimbo, so I omit the very first column of my index, language. Do you know what will be the execution plan of this? Sequential scan, index skip scan, skip scan, okay. It's index skip scan. It's a new feature of Postgres 18. If I use Postgres 17, it would be sequential scan. With skip scan, you can you can skip the leftmost columns in your index. In the execution plan, it's named as index scan, and you can realize that it's a skip scan by the index searches higher than 1. Index searches higher than 1 means that there was multiple navigations through the tree. So the root was accessed 8 times this time. And index skip scan works in a very easy way. I have 57 distinct languages, and Postgres actually do a index scan for every value. So it's like 57 times doing the scan. But because Postgres is smart, if you have multiple languages on the same page, on the very next page, you can satisfy multiple languages by one index navigation. For example, when I showed you the leaf level, there was Arabic, Basque, Bengali, and whatever languages, and they sit on the same page. So I can satisfy multiple languages by the single traversal of the index. So in my case, I did 8 searches, and I hit only 26 pages, just skipping the language. In the previous version, I would do sequential scan, and I would read all the 357 pages. So this is significantly better. Skip scan was presented in Oracle 9i, which was, I believe, released in 2001. So we have a lot of experience in Oracle with the skip scan. And to be honest, I still don't know if for me, in Oracle world, it's a friend or foe. It's sometimes very useful. You just saw the good example. But in Oracle, sometimes happens then, you have enterprise system, your queries are more and more complex, and your estimates go to the hell. So let's say that I have, product in the index, product ID, customer ID, and deleted. Deleted represent the soft delete. So 99.999% of my data has value false, and I have to put this condition everywhere. So let's say I have complex query with a lot of joins, and my table has no other conditions than deleted. With bad estimates, Oracle is capable to do a skip scan for my table, even when product ID and customer ID has terribly high number of combinations. And because the estimate has to be low for this, it's usually as the inner part of nested loop. So I even loop through this skip scan with only one column, deleted equal false, which is 99.999% of my data. And if I hit this issue, it's always P1 because it's terribly slow. It's running for hours usually. So I really wished, and I really wished even today, I really wished to have one thing in Oracle all the time, and that's include. If you have this kind of issue, you can put the deleted into include clause, and you avoid your engine to use this column from the navigation. So the engine can't use deleted even via skip scan. Unfortunately, we don't have it in the Oracle. Okay, index is not for free. There is a bigger disk footprint, larger backups, write overhead, and of course, maintenance cost, vacuum statistics. People usually mention that there is not only the disk footprint bigger, but even memory footprint. I experienced the opposite. I use index tuning to decrease the footprint in my memory. If I have no index, every touch of my movies table is 357 pages. It will be fully cached if it's used very often. If I introduce index for primary key and let's say name, which can be very useful, let's say that I will have 20 pages for each index. So I have 40 pages for indexes. There are trending movies, so you are not touching every page. So let's say 100 pages from the table. So I end up with 140 pages in memory instead of 357 pages in memory. So from my experience, the footprint in memory is usually lower, and I used indexes in the past to decrease my footprint in memory because we are in the cloud these days, and sometimes we have not enough memory in the cloud because the CPU ratio is sometimes poor on the virtual machines in the cloud. While index tuning, you can tune every application. It can be third-party application. If it's your application, you can still use object relationship mapping tool or some other generator for your SQL statements, so you can't change the SQL statements all the time, but you can always add an index. It's very quick, I don't know, tune a query can take you 30, 60 minutes, and you can deploy it immediately. Huge impact. 10x, 100x, 10,000x, it's common for proper index tuning. And because you don't touch your SQL statements, the result is the same. You can't introduce any new bugs. So I really love index tuning. And it's because I built a DB booster. It's an automated indexing tool. In average, we speed up 10% of the slowest queries. Average speedup is 217x. That's like 3.5 minutes to a single second. It's a very straightforward tool. You pick your queries. In this case, I use the top 30 queries from the PG stat statements, check them all, hit optimize, and it's running a while. And suddenly, I got the index definitions. So it's a very straightforward tool with only purpose to give you the missing indexes. We offer a free tier. So instead of definitions, you see just the number of indexes we believe is missing in your system. This leads me to the final topic in my presentation. I believe these tools like DB Booster or DB Tune are awesome. They help you automate performance tuning, which can be challenging if you have a lot of customers or you lack some knowledge. But from my perspective, the future is self-tuning databases. I called that in the past autonomous database, but Oracle is using this word for different purpose, so I switched to self-tuning databases. And I believe it will be built internally, because from the external side, you have still limitations what you can tune, because you miss some information. The self-tuning database should fully adapt for different workloads. So if you change your workload, it should fully adapt to the difference in the workload. And from my perspective, I believe these systems won't be related to LLMs. And the key is, of course, automation. So I tried to be really fast because we were delayed, so I was successful in my approach. So if there are questions, I will give you a space for questions, or I can do a summary. It's up to you. So any questions? Does it work? But it looks there are no questions, so. Okay, so that's everything. Thank you very much.